Okay, so today we're going to talk about sound and light. You were supposed to look at light vocabulary yesterday when you were doing your Wednesday work. And today what we're going to do is we're going to look at waves and how waves work. So I'm going to go ahead and share my screen. And again, you need to keep up with these notes. For the people that are at home, you're going to see the notes on Cami. People here, you have it on paper. So waves are a form of energy. It's just like heat or electricity. It's something that allows energy to flow. And energy is pretty much the movement of particles. There are two main forms of energy that travel in waves. That's going to be light and sound. And that's what we're studying for the next couple of days, light and sound. So light and sound travel in waves. Now, the first type of wave is going to be like a light wave, and we call it a transverse wave. It's the one that you see at the bottom of the page. So when you look at this, I'm going to move it back, don't worry. This type of wave that goes up and down, that's going to be what we call a transverse wave. It goes up and down, and you can draw a little picture beside it. The other type of wave is called a compression wave or a compressional wave. So I'm going to write the word compression, and then in parentheses, I'm going to put an AL because it can either be pronounced a compression wave or it can be a compressional wave. And when we talk about a compressional wave, it's going to look like a slinky, or it's going to look like a lot of dots where there are parts that are pushed together or pulled apart. So it's going to look like this. It can look like particles that are pushed together and pulled apart, or like a slinky that's pushed together and pulled apart. We call that a compression wave. So compression waves have to have matter to travel through because it's the little particles of matter that get pushed together and pulled apart. That's the way that sound travels. Okay? However, it's really hard to draw a compression wave. So if I'm trying to draw a compression wave, I either have to draw a slinky or I have to draw dots where a lot of them are really close together and then some are far apart. And it takes a lot of time. It's easier to draw transverse waves. So we can represent all types of waves by looking at a transverse wave. Okay. When we talk about the wave that's a transverse wave, there's different parts. The highest point of the wave is called a crest or a peak. And normally I will use the word crest, but it's the same thing. Crest and peak are synonyms. It's the highest part of a wave, crest and peak. So if we look at the diagram at the bottom, you'll see an arrow that's pointing to this top point of the wave. That's what we're going to label as a crest or a peak. Make sure you're choosing the arrow that's pointing just to that top. We are not choosing this one. That's going to be something else. Y'all know Woody Woodpecker, like the cartoon? He has that red part on top of his head. That's called a crest. Whenever you see a bird with feathers on their head that stick up, that's called a crest. That's a way to remember that. Now, the bottom part is called a trough. It's like a pig trough. And when you think about a pig eating out of a trough, they eat out of that rounded part at the bottom, right? That's the same of a wave. T-R-O-U-G-H. It looks like the word tro or something, but it's pronounced trough. And when we look at our picture, the trough is going to be this bottom point of a wave. Trough. T-R-O-U-G-H. There are two other main types of a wave. The distance between two crests or two troughs is called the wavelength. It measures how much energy the wave has. The closer together the wave is, the more energy it has. The other part is called the amplitude, and it's the height of the wave. Amplitude. So we have the wavelength and the amplitude. And we're going to label those on the bottom here in just a second, after everybody gets that written down. So from one crest to another, so you see we're going from one crest to another, that's called a wavelength. It can also be one trough to another. We can go from here to here, and that's also a wavelength. So a wavelength's one crest to the next or one trough to the next. And it can be any two troughs or crests that are right beside each other. It can be from this one to this one or this one to this one. And the closer the wave is together, the more energy it has. Now, the last thing says the blank of a wave is how many crests or troughs pass a point in 1 second. The higher the frequency, the smaller the wavelength. We call this frequency. Frequency is how many times the wave goes up and down in a second. And if this whole wave passed a point in 1 second, the frequency would be how many times it goes up and down. Frequency. It's spelled right here for you up here. That's probably the easiest way to see where it's spelled. You're just writing it again there. So those are the main parts of a wave. Wavelength, crest, trough, and then over here is going to be the amplitude, the height. So this is showing how tall the wave is, and we call that the amplitude. Normally, if I have you label a wave like this, I won't include frequency. It'll be the wavelength, the crest, the amplitude, and the trough. And you don't need to write crest and peak both. You usually just write crest. Okay, let's go to our next page. So again, when we look at a light wave, it goes up and down like an ocean wave. That makes it a transverse wave. Light is a transverse wave. Do you see that light ends with a T? Light, transverse. Light, transverse. Sound waves are compressional waves. They either look like a slinky over here, or they look like the dots that are at the bottom. Light travels much faster than sound. That's why we see lightning before we hear thunder. That's also why we see fireworks before we hear them go off. So light is a very fast wave. It travels much faster than sound. All light travels at 300,000 kilometers per second. It doesn't matter what type of light it is. It could be a laser. It could be the light from the sun. It could be a light from a flashlight. It could be like ultraviolet light that gives you a sunburn. All of it travels at the same speed. If we think about that speed, that would be being able to go around the Earth about 13 times in 1 second. So if something could travel around the whole Earth 13 times in 1 second, that would be how fast light travels. It takes light from the sun about 8 minutes and 23 seconds to get from get from the sun to the Earth. So that kind of shows you how far away we are from the sun. Sound waves travel differently in different substances. It ranges from 300 meters per second to 1,200 meters per second. So you can see the difference, right? And this is meters, and this would be kilometers. So we would have to add 3 more zeros to this to do meters. So it's 300 million meters per second and 300 to 1,200 meters per second for sound. So sound's much slower than light. Temperature and state of matter affects the speed of sound the most. So since sound has to go through like matter, how close the particles are together affects how fast it moves. Okay? Number 5, it says blank travels the best through a vacuum where there is no matter. That's light. Think about outer space. There's no matter in outer space unless you hit a planet or a star or something. So light travels really well through a vacuum. However, sound needs matter to travel through and travels fastest through solids because the atoms and molecules are close together. Okay, so what we're going to do is we're going to draw a transverse wave on top of these waves down here. Okay, we're going to start with the bottom one first. So look what I'm doing. Do you see the dark areas? We call those dark areas compressions, but they're kind of like the crest of a transverse wave. So on top of each of these compressions, we're going to put a dot in the dark part. Okay? So in the middle of the dark part, I'm putting a dot here, dot here, dot here, dot here, and a dot at the very end because the dark part's kind of at the very end of that wave. We call that a compression. So even though we called it a crest on a transverse wave, it has a different name for a compression wave. Did everybody draw those 5 dots? We're going to draw 4 dots where they're spread apart, right in the middle of where they're spread apart. This is a weird word. It's called rarefaction. And you can see it written on your note sheet right here. Rarefaction, compression. There's only one compression. Rarefaction. Now look what happens when I connect those dots. It actually makes a transverse wave, doesn't it? Yep. So I want you to connect those dots. It is. So we can look and we can represent a sound wave with a transverse wave, even though we know it really isn't a transverse wave. It's really a compression wave, but we can draw a transverse wave on top of it. However, when we look at the top part, we do not call that top part a crest here. We call it a compression. So the top part is called a compression. And then the bottom part, where it's spread apart, is called a rarefaction. But it still has wavelengths. From the middle of one compression to the next, or from the middle of one rarefaction to the next, is called a wavelength. So here's a rarefaction to a rarefaction, that's a wavelength. Here's a compression to a compression, that's a wavelength. And if you're seeing where those are spelled, they're also spelled for you, like rarefaction spelled for you right there. Compression is spelled for you right up there. Now, you do not need to draw this, but I'm just showing you, okay? You can also draw one on top of the slinky. Where the slinky's pushed together, I would make a crest. Where it's pushed apart, I would make a trough. But you don't need to do that one. Okay, so what you're going to do is I'm going to give you a sheet here in a second, but I'm going to do one part of the sheet with you, okay? So I'm just going to show you how to do this one part, and then you're going to use your notes to do the rest of these sheets, okay? Maggie, will you pass those out to everybody? Ron, can you pass those out to everybody? So the first worksheet I want you to look at is the one that looks like this. Thank you. Okay, so when we look at frequency, first of all, when you look at this side, you're just labeling the wave like we did on the first sheet. And down here, you're labeling these as transverse or compressional. Thank you. You're not labeling them as light and sound. You're using the word transverse, compressional. Use your notes. Now, this is what I want to show you real quick about frequency. When you're measuring the frequency of wave, you're basically measuring how many wavelengths there are. Okay, so when you see the word frequency, you're measuring how many wavelengths. Look what I do. I circle whether it starts with a crest or a trough. That stands for 0. I do not count that for 1. That's why I circle it. Then I count the number of jumps. 1, 2, 3, 4, 5, 6, 7, 8. I'm counting the number of times I jump. I do not count this as 1. I count this as 0. Okay? And you need to make that circle. So everybody circle the crest on this one and then count how many jumps you make and draw it with your pencil. 1, 2, 3, 4, 5, 6, 7, 8. The frequency of that wave is 8 hertz. And hertz is just a unit like degrees Celsius or meters or centimeters. It's just the unit that you use.
It's like ice cream.
It does, kind of. Now, when you do one that starts with a trough, you do the same thing. You just do the jumps on the bottom. This is a 0. And we jump 1, 2, 3, 4, 5. This time I did 5 jumps. So I'm going to write 5 hertz. The mistake that people do with this is they count the first one as a 1. They say 1, 2, 3. If you circle it, that circle represents 0. And you'll remember not to count it, okay? So when I see you do those, you need to make sure that you circle each one of those, okay? So you're going to finish the rest of the sheet. You're going to do the rest of those. On the other sheet, we're just going to label the bottom here. We're going to label this as a compression. We're going to label this as a rarefaction. And then we're going to label one compression to the next or one rarefaction to the next as a wavelength. We're not worried about amplitude for this one. In a sound wave, the amplitude or the height affects the volume, how loud it is. And I'm going to leave that up there, but at this point, you should have all the information you need to complete the worksheets.